Okay, so today we are going to finally start the neural networks, and today we will mostly talk about the backpropagation, which is one of the most important concepts when you learn about neural networks for the first time. So I guess many of you are already familiar with these things, so please take this as an opportunity to review. And these slides are modified from the Stanford class by Professor Fei-Fei Li. So yeah. So where we are, our image classify. We talked about image classification model, which is the so we had to choose model, which is the linear model. So our given a data set, we model it by multiplying some weights element-wise and add some bias, and that was our model. And we decide the loss function. So here we decided to use the softmax loss function. And another thing we had to decide was the optimization. So we learned about stochastic gradient descent. So in the last lecture, we showed how the machine learning model training is done. And we had to decide all of these elements. So we now have an image classification model, and we know how to evaluate, how to train them, and how to optimize them. But so far, we have used the linear classifiers, but this is not a perfect way or powerful way of modeling images. So here's the reason. We talked about visual interpretation of our weights, the trained weights, something like this. But linear classifiers learn only one template per class. So if the images are more like homogeneous, for example, here we can conjecture that the car images we have seen when we train this model was more like, looks like this. They are front side of the car because we see some windows here, and the color of the car was white and red or black, but we probably they didn't have that much blue cars or yellow cars or other colors of cars, which is we can conjecture from this the template. But here, the deer or birds, we cannot actually guess that this is birds because they probably have very different kind of birds pictures. So other than the backgrounds, which is greenish, it was it's really hard to capture that this is birds. So there may be different subcategories of the birds, and this only one template may not reflect all the variance or intra-class variations. We showed about that at the beginning of the particular class. So it would be nicer if we can have multiple templates rather than just one. And geometrically speaking, linear classifiers can only draw linear decision boundaries. So from the previous lecture, we have seen that the model parameters are always linear hyperplane within that Euclidean space. And because all the hyperplanes are linear, when they meet, the decision boundary is always linear. But data points are not necessarily distributed in a linear hyperplane. Something like this or this or this. These may look too artificial, but they actually have some nonlinear relationship between the data points when they are scattered in the actual the Euclidean space. So how can we model these nonlinear relationships discovered in the data set? One idea is actually not using the XY coordinates directly, but we may send it to some other coordinate systems. For example, these are actually similar to this one. So one class is located near the origin, and the other class is located far from the origin. So when we use the Euclidean space as it is, no linear classifier can perfectly classify these kind of data sets. But when we convert this to polar coordinates, which is r and theta, r is the radius and theta is the angle from this line. So we can actually see that this data set is linearly separable in these polar coordinate systems. So if we send some data set to another coordinate system, which makes this data set linearly separable, then we may use the linear classifier to perfectly or quite well classify in the data set. But is it always possible? Probably not, right? This one was a quite easier example that we can find these polar coordinates. But what about this? Or what other data sets which is much more complex? What should we do? So it's usually possible if we increase the data, the dimensionality of this Euclidean space. For example, these data sets are in two-dimensional space. We have two axes, so it's two-dimensional space. But if we map this to higher dimensionality, at the extreme, if we have the number of dimensionality same as the number of data points, then we can always make that as linearly separable because we can send each of them to different dimensionalities. But that's too extreme. But it's usually possible if we just increase the number of dimensionality to make it linearly separable, or at least close to that. So how can we represent an image in as a feature? So people has shown some ideas like this previously, before the deep learning era, like something like this, color histogram. So how to represent the feature, this image as a feature? This idea is classifying the color in each pixel, and we just draw a histogram like this to represent its distribution. So in this example, we divided all the possible colors into 10 buckets. And if each pixel corresponds to each bucket, and we increase the count of that. So we know that this picture is more like greenish image with some yellow-green or some more like blue-greens. But we know that these colors are more frequent than others, like reds. So this may be one good representation of the image. But what do we lose here? We have just the distribution of the colors, but we lose the shape of that, right? This histogram is independent of the location of those pixels, actually, when we found those pixels here. So gradient orientation per patch is, we divided the image into multiple patches of small images, like, for example, 8 by 8 or 16 by 16. And we compute the direction of the dominant color change. So for example, in this particular patch here, the direction of the change is like that, right? So we compute the edges. This is just a high-level idea, but these are not the important part of this lecture. But I'm just showing what we have tried before we have the deep learning. So they learned how to, they kind of discovered these are a good feature to represent the some properties of the input image, and they have used this for image modelings before. But so here's what we are doing so far. Given an input image, previously we were trying to learn the image models directly from X. So we learned some function fx, which directly maps to label, but we have learned that that's not a good idea always. We kind of say that we never use the pixel distance to model the images. So instead of that, we extract some features from this image. So we have an image feature called z here, and that may be some vector, like the histograms here. And then we learn some classifier on top of this feature. And this function outputs the probability or score for each label. And we train only this part. Based on the errors we have made, we update the model using stochastic gradient descent. And we repeat this only here. So this part is fixed or frozen. But the idea of deep learning or end-to-end learning is like this. Should we use some deterministic function always to extract the features? Or can we actually update this feature extraction part as a parametric model using the loss we have in the end. So the end-to-end means from the image X to label Y, when we have any loss in this estimation from the classifier, we backpropagate that loss or error to the very beginning of the model. So can you actually automate this part and learn the parameters from the data instead of the predefined functions like histograms? So that's a good idea, and that is the kind of trend in deep learning. But is it always good? We may say no, because in ideal thinking, actually, in ideal space, if we can learn anything from the data set, that would be great, because we, as a human, we don't have to decide except for the shape of the model. But if we do this, actually, we need too many data set. Cost of dimensionality is one reason, and the pattern we have to discover is too complex. So we require more data points, and that is followed by more computing powers and carbons and all the things. So it's not always a good idea to use the end-to-end learning, but if we have some domain knowledge we can reflect to reduce the computation, actually that's a good thing. But in this course and also in other machine learning courses, we always try to learn something end-to-end. But I wanted to mention that that's not always the perfect way of solving some problems. So anyway, that was just the introduction. And we're going to learn about neural networks. And so far, from now on, we are going to try to make it everything end-to-end. So just keep in mind that that's not always the best thing, but we are going to learn how to do that. So neural networks comes from the idea of perceptron, which mimics the function of our neurons in our human body. So I'm not a biologist, and I'm actually bad at it. So I don't know the details how these are actually working. Maybe some students in this class know more than I am. But yeah, so this is a neuron, and from the cell body, at the end of the neuron, we have something called dendrites, and it takes the impulse from other cells, and it's kind of a receptor. So it takes the impulses from other human cells, and there are multiples of them, and they are actually combined at the start of the cell body. And if this impulse is strong enough, it fires. Otherwise, it ignores. So if it fires, then that impulse carried away from this cell body to some other cells. And at the end of here, another dendrite from other cell body is connected to here. So the information from other cells are carried to other cells through these neurons. So neural networks basically mimic what we do in these human cells. So from other neurons, we take some signals or impulses, which is denoted as X, X0, X1, and X2. These are input to this cell or neuron. And in each synapse, it's modeled as weights. So each of these are multiplied with some weight values, which is W0, W1, and W2. And they are added to this WIXI, and we sum over all of those. So this part actually mimics here. So this cell takes multiple impulses from other cells, and they are combined here. And if they are strong enough, then it fires. Otherwise, it's not. So that firing part is determined by this F, which is activation function. And if that output is fired, then we have some outputs, and it goes to other neurons or perceptrons as an input. So this, you can see that this is kind of mimicking what we have in our human body. But actually, this is not a new thing. We are already doing this. In the last lecture, we learned a linear classifier, right? So we had X as input, which was image. And we multiplied that with weights, right? So Wx, this part is actually the linear part of our model. And in the end, we had some activation function. And we use the softmax function as our activation function. So that is an example of activation function. And then we had the output exactly in the same form like this. Or if we do the linear regression, this part is, instead of the sigma, here we had the identity function, which means it doesn't do anything. Then that is equivalent to linear regression, which most of you are already familiar with. So perceptron is actually nothing. It's just nothing but weighted inputs based on the weights we have already learned. And then we activate it with some nonlinear function, and we just fire that. So this is the simplest neural networks, which corresponds to one neuron in human body. And we denote this to these kind of forms. So suppose we have an input vector, x. For example, its dimensionality is 3072, which is the image size of 28 by 28. And we have the weights, which maps this x to the number of classes or the output sizes, which is 10 in this example. So what should be the dimensionality of these weights? X is d-dimensional vector, and S is c-dimensional vector. So we have to map this by multiplying W, which is size of C by D. Okay. So Wx is C by D times D by 1. So output should be C by 1. So that is here. Or we can draw this way, which is more intuitive. So X has 3072 numbers. And each of those numbers are multiplied with some weights, which is represented as an edge here. So this is W1, W2, W3, and W3072. Each of these are multiplied with the values in the input and summed over to, and then followed by nonlinearity. We have this output. And we have 10 of them corresponds to 10 different classes, which is same as what we learned in the linear classifier lecture. Okay, so this is a neural network with a single layer. So we learned about the perceptron, and we basically have 10 independent perceptrons to output 10 class scores. Okay, and now using this perceptron, multi-layer, the single layer perceptron as a building block, we can actually stack them to have multi-layer perceptron. So in the first part, we map the d-dimensional input vector to h-dimensional, here 100, 100 space. And then it's another vector of 100 dimensions. And then we send it to 10-dimensional vector of scores. So instead of doing this at one step, we may do this into 2 steps like this, right? So here again, the W1 is h times d-dimensional because we have to map the d-dimensional vector to h-dimensional vector, right? And then W2 is c times h because we map h-dimensional vector to c-dimensional vector. And we can draw another way like this. But what's the difference? Actually, they are the same thing because this is represented as W times X. And here it's W2 times W1 times X. So if we define W2 times W1 as just W, then they are actually doing the same thing. So why should we do this multi-layer perceptron? What's the benefit of that? So these are equivalent only if we don't have nonlinearity. So that's why we are adding nonlinearity at the end of the layer, as which is called activation functions. So yeah, as I said, this is exactly the same as just Wx. So we don't have any benefit by stacking these multiple layers. But if we have some nonlinear activation function after each layer, then we have actually represent nonlinear relationship between x and fx or y. And we do actually have benefit of doing this. So these are the examples of the activation functions. One is the sigmoid we have learned in the previous lecture, remember? So these look better because it provides some probabilistic interpretation because it outputs always between 0 and 1. Or tangent H, it provides both positive and negative outputs. Sigmoid doesn't, right? So tangent H is another widely used activation functions. And ReLU, rectified linear units, these are positive values are just output as is, and negative values are just cut down to 0. So I will not go into the details of these activation functions today, but we are going to learn more about these in lecture 6 in next week. So we learned about multilayer perceptrons, and here is an example which is 2 layers. So let's see the codes together. So let's define the data set and labels and weights. So data set is we have n data points, and actually here 64 is the batch size, but or it can be just the entire data set. But let's say this is 64 examples. And D is the input dimensionality. So input image or input vector is represented as 1000 dimensional vector. And Y is the classes, the labels. So N times C. C is the number of classes. We have 10 classes. And W1 and W2, the shape we already showed in the previous slides. So it should be D times H because the first layer maps the D-dimensional input vector to H-dimensional space in the hidden space, or you can actually define H times D. Yeah, we have to check that. And then W2 is H times C because we map from H-dimensional space to C-dimensional space, and we define some learning rates. Again, this learning rate should be determined by cross-validation. So here, this part is forward pass. So we compute the output using our current estimation. So the model is like this. It seems it's using sigmoid function as its output, the activation function. So this is the shape of the sigmoid. Remember that? Like this. It's implementing basically this function. So 1 divided by exponential of minus x dot product with W1. So here, this input is x, and W1 is multiplied as dot products. And this is called H, and the prediction Y is H times W2. So that's basically what we are implementing here. So A1 is the sigmoid function, and A2 is nothing. So we have this identity function for H2 here. So when you compute the loss function, because this is a regression, we are using squared loss function. So prediction minus ground truth, and we sum all of that. So this is basically the squared loss. And it prints the loss at time t. And then this what we need to do is, remember from our previous lecture, we do the forward pass to estimate using our current model, and we compute the loss based on that, and using the loss to update the parameters to make it better, right? To make it better, we are using gradient descent here. So what we need is the gradient, right? What was the gradient? We quantify how much this model is good or bad using the loss function. And using that loss, we need to determine how much each parameter is in charge of that error. And we need to update that parameter to the correct direction, right, using the loss. So this part is doing that. And what we needed that? We needed to compute the derivative, first order derivative or gradient of those weight values. And because we know these are the squared loss functions and we know all the form of the functions, we just mathematically solve the gradients and we coded that here. So That was the main way of doing this updates when we use this, when we know the form of the function and it's not very complex. So let's see in more details. So this is our model. So two-layer perceptron given input x, and it's multiplied by W1 and goes through the sigmoid loss, the activation function. Then we have W2 multiplied, and then we don't have activation function here, so the output is y. And we compute the loss function by squared loss. And what was the gradient descent? That you may remember that this was copied from the last lecture. So each parameter value, theta, which corresponds to one value in W, is updated by the cost function or loss function, which is L here, is taking the derivative with regards to that particular weight value, and that gradient is updated in this way. That was the gradient descent we have learned in the previous lecture. So what we need is this part, actually. We need to compute the derivative of this with regards to W. So each gradient indicates how much that particular weight contributed to that incorrect prediction, and we would like to compensate it by updating to the opposite direction. So this is our example. So the loss function is the squared loss here, and when we take the derivative with regards to y hat, then it's like that. I guess all of you are familiar with this derivatives. And when we do this, the partial derivative of loss function with regards to W2, then using the chain rule, we have this. So first part is same as this. And second part, we take the derivative with W2 here. We have only the right one here. And do the same thing. So we define this part as H. And when we take the partial derivatives, we will have these three components, and they are all multiplied. So because of the time, I will not go to all the details, but please double check if these are correct and just follow the math here. And this part, actually, you may use this fact that when you take the sigmoid derivatives, then it's itself times 1 minus itself. You maybe verify over here. So this is what we can do with analytical mathematical derivation. But unfortunately, this becomes too complex when we actually have multiple layers. For example, this is what I studied in when I was in graduate school. And this is actually even more difficult things for LSTM, backprop. So it's this, you can see that you have to compute all of these partial derivatives with hands. What about for even more complex neural nets like this? Actually, we are going to learn these models in lecture 8, but you basically cannot compute all the gradients using your hands. So what should we do? That's why we would like to learn about backpropagation. So computing gradients for neural networks easily. So this is really important when you learn about neural nets. So we first represent our model as a graph like this. We have three variables here, W, X, and B. And W and X are multiplied, and then it's summed with B. So that's what we have on the output, okay? So we first do the forward pass to evaluate our prediction using the current weights or current values of these variables. Then we compute the loss, and that loss is backpropagated to all of these previous nodes with how much it was in charge of that error. And based on that, we would like to update that. So because of the chain rule, we need partial derivatives, which appears to the right in the right of this graph are needed when we compute in the left. So that's why we are actually backpropagating instead of forward pass when you compute the gradients. So we are going to see some examples. Suppose that we have this model x, y, z, x plus y times z, and we suppose we have x and y and z with these values. So in the forward pass, we just do this, right? We just input these and compute the output. Let's define this part as q. So the output value f is minus 12. This is just elementary school math. Let's do the backpropagation from the end of this network. So what we need to have at the beginning is this. At each point, we like to have the partial derivative of the output, which is the loss function in actual neural networks, with regards to each variables, here x, y, and z. So in the end, at the end, we start with partial derivative of f divided by partial derivative f, which is always 1. So at the end, we this partial derivatives is always 1. And then let's compute here this part. So fz, here f is q times z, and q is x plus y. So this is partial derivative of qz with regard to z. So when you compute this analytically, that is q, which is x plus y, right? And x plus y is 3. So that's how we have this partial derivative using this formula. And what about this part? That part is qz, right? This was qz. And we take the partial derivative with regard to q, then it's z. So what's the value of z here? Minus 4. So here, this is minus 4. The partial derivative is minus 4. What about here? We need this partial derivative of f with regards to x. And using the chain rule, we need this fq and qx. So the previous part, fq, is we already have computed that. That is minus 4. And what about this part? Partial derivative of q with regards to x. Q was the x plus y. So x plus y, partial derivative with x, that is y, which is, no, sorry, this is just 1, it's constant 1. So z times 1, which is minus 4. It's here, and in a similar way, we have minus 4 for this y. So we can compute partial derivative with the final loss function, loss value, with regards to each variable in this way, using this graph. And because of the chain rule, you're going to need partial derivative you already have computed at the later stage of the network. And we backpropagate in that way from the loss function to the beginning, which is the input variables. So we can summarize this as a chain rule like that. In each node, you have some function, and it takes multiple inputs, let's say x and y. And when you do the forward pass, you compute based on what this function defines. For example, x plus y, then you have the output z. When you backpropagate, each node receive upstream gradient, which is the gradient computed later nodes, at the later nodes. And this is backpropagated. And within this f, you have the local gradient, how much this x affected z, right? And you compute these local gradients, and then to each input edges, you multiply this upstream gradient times this local gradient. So that is partial derivative of loss with regards to this input variables. So in this way, the entire loss function, the entire objective function is connected like this graph. And in each node, you take the upstream gradient and multiply it with the local gradient, and then it's output to each node. And in this way, you can go to the very beginning of the network. So let's take another example. I usually ask this to each student, but because of the time, let me just quickly go over this example. But please review this before in the next lecture. So here, this is the function f with x and w, and this is the logistic regression. which is the inner product of these vectors plus bias, and it takes the sigmoid after that. So this is the computational graph of this model. So we have W0, X0, W1, and X1 and B as the input variables. And using this graph, we finally have this output. Okay. Suppose we have these values as input. And then we do the forward pass. This is just a math. You can just compute. Forward pass is easy. And the output is given as 0.73. Okay, let's start from here. From the backpropagation, I told you that at the very end of our model, it starts with 1, right? Always it's 1, because it's take the partial derivative with itself. Then let's compute this. What do we need here? Please remember that what we had for each node in the previous slides, upstream gradients multiplied by local gradients. Please remember that always. So what is the upstream gradient here? It's 1, right? It's coming from the later nodes. So this is upstream gradients. And what is the local gradients? We have to take the partial derivative within this node. So because the function is 1 over x, its derivative is this, minus 1 over x squared. And then we have all of these values, right? Upstream gradient is 1, and local gradient is this. And we know that the input x is 1.37. So we take that value to have this output gradients, which is multiplied by these two. Okay? Then let's do the next one. Now, what is the upstream gradients? Minus 0.53. This is the upstream gradients. And here, this node is fx is x plus 1, right? So what is the local gradients? We take this gradient derivative, then we have 1, right? So now local gradient is 1, and upstream gradient is minus 0.53. So they are multiplied. So output is still the same. So in this way, we can repeat this. Please do this as your exercise. We repeat this for the upstream gradients and local gradients at each node, and we can compute its output. And we do this, repeat it again and again to have the output gradients. And this part is a little bit tricky. We have the addition of two different functions. So f is x and y, and they are summed. And when you take the derivative over x and y, and then we have both of them are 1. So multiplied by upstream gradient, which is 0.2, they are kind of distributed to each subtree of this model. And here is the same. We do the same thing. So it's 0.2 is distributed. And then this multiplier, the function is w times x. And when we take the partial derivative with each other, then the survivor term is actually the other way. So for w part, we have x value and vice versa. So when they are multiplied with the upstream gradients, they are multiplied, and we have these outputs. I went over this too quickly, but please review these slides, and please do it yourself to get familiar with this, because this is super important. And this is the summary, which we can discover in the gradient flow. So when we have addition gate, the gradient is actually distributed, as we just have seen previously. And multiplication, and then it's swap multiplier. So which means this 5 is multiplied with 2, which is the input value in other edge. And here it's multiplied with 3, because 3 was the input from the other input to this node. So it's called swap multiplier. And copy gates, which is actually, this is the opposite to this. So the gradient is coming from different direction, and they are merged, then the gradient is summed. And the max gate, the gradient goes to where the max value was actually came from, here 4 and 5, we had 5 because this was larger. So gradient actually goes through that way. So yeah, these are just a summary, and you can actually practice with actual examples like this in the previous example. More familiar with this. So once you are familiar with this, get familiar with this graph-based analysis of these local gradients and the upstream gradients and how to compute these gradients at each node, actually coding it is just straightforward. So forward pass is these green things. So input 5 values are like that, and then you just follow the formula, right? Just multiply these two and multiply these two, sum those two, and then sum with b, and then take the sigmoid function. So this is the forward pass, right? Gradient computation is the same. You start from the last gradients with this loss function that is always 1. And then each of these are just computed as what we just done so far. So this part, gradient S3, is using this formula. This is the local gradient, and this is the upstream gradient. So they are just multiplied. And gradient B is here, which is same as S3 because the local gradient is 1. So this code is just straightforward if you're already followed how we computed the local gradients and upstream gradients. So please review this by yourself and understand how this gradient computation is done here. And in the next lecture, I'm going to ask this. Okay? So in the next lecture, we are going to extend this to vectors and matrices. Today, we just saw some examples with the scalar values, but actually what we deal with in actual neural networks is the vectors and the matrices. They may look much more complex, but the basic idea is the same. So I strongly encourage you to review these slides. And also, I uploaded the lecture notes for each lecture. So please read that. It's not very long, and it's easily explained, all of these things. So please review the course materials and get familiar with these. And in the next lecture, I'm going to test you with these things. Okay? Any question today? If not, let's finish the lecture here. And if you have any additional questions, you may ask me after the lecture.